So just to review what we did before, let me just get this started. We've gone through what acids are, what bases are, the fact that water is amphoteric. We talked about strong versus weak, and then we talked about conjugates. I'm going to get back to conjugates, why the weak acid-base conjugates are important in just a moment. But before we do that, let's look at just some acid-base reactions. Acids and bases neutralize to form water and a salt. Typically, it's really a double replacement reaction. If you think of double replacements like ionic equations, and you did a lot of that. Remember, in an acid, hydrogen is acting like a metal, and hydrogen would be a +1. So what happens is H goes with the OH, and then you have YX. So for example, you guys can try these. This should be really easy for you because you've done this a bunch of times. But I'll give you a, hit pause and try this on your own. All right, I'm sure this was pretty easy for you, but we'll go through it real quick. And so what happens is the H goes with the OH. If you prefer writing water as HOH, a lot of people write it, organic chemists write it that way. It's very helpful. And then NaCl, and of course here, right, H with the OH, and then we have to balance it. Now, let's talk about pH, and then we'll get back to conjugates. All right, we're going to do a little bit more here. So pH is technically a measure of acidity and basicity. And the lowercase letter p is actually a mathematical function. So p means negative log. Just like x means multiply, p means negative log. H3O plus in brackets, this means molarity of H3O plus. So it's the negative of the log of the H3O plus. And we'll do some calculations later. We're going to do this qualitatively first. And you can take the p function of anything. So for example, there's also, okay, let me just go through the slides. All right, you could have POH. That would be the negative log of OH. You could do P of Cl, negative log of the molarity of Cl. Now, the couple things about this, if you increase the amount of H plus, right, H3O plus, this goes up, that means the pH goes down because it's the negative of the log. Right, so acids have low pH. If you have a basic solution, base hydroxide will react with H plus, which means it's going to lower the H3O plus. Remember, H plus and H3O plus are synonyms. It's going to lower that, which will make this go lower, which means the negative goes higher. That means pH will be higher. Bottom line is pH of 7 is neutral. Why that is because at 7 you have equal amounts of H and OH. Right? If it's below 7, it's acidic. If it's greater than 7, it's basic. And the lower it is, the more acidic, the higher it is, the more basic. In addition, this is a log function, so that means pH 6 is 10 times more acidic than pH 7. pH 5 would be 100 times. They're all orders of magnitude. All right, now we'll do the math with this later, towards the end. Okay, now let's talk about buffers for a moment. So what is a buffer? In Chem 201, you're going to do all the math with all of this stuff, but right now we're just getting the qualitative. A buffer is a solution that resists changes in pH. So in an acid, we have H plus ions, and in a base, we have hydroxide ions. But if you dump these into a buffer, the pH doesn't change. Now, why would that be important? Well, let's just look at a biological system. If you think of your blood, okay, your blood has a pH that's right around neutrality. All right. By the way, the concept of the pH of your body is bullshit. There is no such thing. Your body has different regions of your body have different pHs. Your stomach has a very low pH. Your small intestine has a high pH, not really high, but maybe like 8, something like that. Certainly higher than your stomach is like pH 1 though. So the concept like alkaline water, it's just ridiculous. As soon as it gets into your stomach, it's going to be it's going to drop right down because water doesn't buffer. But your blood has a pH around 7. Now, if you eat something acidic or basic, it goes into your blood, yet the pH of your blood doesn't change because it's buffered. Now, why is that important? It's specifically important because in that example, proteins, which are very important molecules, can be very pH sensitive. And your blood has a lot of proteins in it, but one that's interesting is hemoglobin, which is an oxygen transporter. And if the pH of your blood was to change, hemoglobin would cease to function. And if hemoglobin doesn't work, either do you. So how can your blood take up stuff that's acidic? Like if you eat an orange, it's acidic. Or if you have something alkaline, like some vegetables can be very alkaline. All right, and yet the pH of your blood doesn't change. And the answer is it's buffered. So what I mean by this is if I was to draw a graph, if I took a flask and I had water in it and I added acid, like with a dropper, the pH would drop very, very quickly, right? If I took a flask with a buffer in it and I added the same amount of acid, let's say I added this much acid, okay, see how the pH of water drops a lot, but the pH of the buffer barely drops? Okay, and the slope might even be flatter than this. So it slows down the change in pH. The same buffer can do it with base. And by the way, don't get the idea that it has to stay around neutrality. It depends on the buffer. Some buffers will stay at neutral, some buffers will keep it at 2. Just depends. All right, but again, if I had a flask with water in it and I added a strong base like sodium hydroxide, the pH would go up very quickly. If I had a flask with a buffer in it and I added a base, the pH goes up, but not nearly as quickly. So that's what buffers are. That's what buffers do. Now let's look at how do they do what they do when they do what they do. So how do they do it? Well, if a buffer is going to neutralize acid, it has to have a base in it. And if a buffer is going to neutralize base, it's got to have an acid. How can I have an acid and a base in the same container and have them not neutralize each other? And the answer is it's a weak acid, weak base conjugate pair. If I transfer an H plus from here to here, you can see that you'll get the same thing. So a buffer, the key is it's a mixture. It's more than one thing. So it has HA to neutralize base and has A minus to neutralize acid. So let's look at how this works, all right? So if I had a buffer and I added H plus, the H plus is going to react with the basic portion of the buffer, and you'll see how the H plus gets neutralized, so the strong acid gets neutralized into a weak acid, all right? And if I have the same buffer, if I add strong base to it, hydroxide ion, it's going to react with the acid component of the buffer, right? So this will go here, and we get water and A minus. And so what happens is the strong base gets neutralized and becomes a weak base, which does not influence the pH quite as much. The key is it's two separate reactions, buffer plus acid, buffer plus base, because a buffer is more than one component. Students sometimes try to write it as one reaction, and that doesn't work. So try this one on your own. This is actually the one on the homework, but give this a go on your own. Okay, you hit pause. All right, so if you're back from pause, let me show you how to do this. So what you want to write is the acid component of the buffer reacting with base, use hydroxide for base, the basic component of the buffer reacting with acid. Now, by the way, how do I know which one's the acid? The acid will always have an extra H plus compared to the base. So this would be the answer. I take the acid component of the buffer, react it with base, use OH for base, make your life easy. And then we transfer a proton from here to here, and we get H2O, and we get the weak base. So this is neutralizing added base, and this is the buffer, the base component of the buffer, neutralizing acid. Make your life easy, do it with H plus, and H plus goes here. See how it's always transfers of H plus from an acid to a base, from an acid to a base. Always, always, always. All right? Okay, the last set of material here is going to be pH calculations. So like I said earlier, pH is P, the lowercase p means the negative log. So pH, negative log of H3O plus or H plus. POH, negative log of OH. So how do we do pH calculations? The best way to do it is just for me to go through an example. All right, so we'll just go through an example. So if I ask you to calculate the pH of 0.020 molar hydrochloric acid, well, where am I going to get the H3O plus? That's nowhere to be seen. I'm going to get it stoichiometry, all right? And remember, if it's a molar solution, it's in water, and we know what acids do in water. So what we're going to do is start with a balanced chemical equation, set up a table. So this is shorthanded stoichiometry. At the beginning, I have 0.020 molar hydrochloric acid, but it all reacts. And so at the end, this is all gone, and I have 0.020 molar H3O plus. The chloride doesn't matter, but it's good to learn how to set up these tables, because when you do this in 201, this is how you're going to do it. All right, and when you deal with weak acids and bases, which we don't in this class, this is how it'll work. But just to show you where this number comes from, right? I had 0.020 molar hydrochloric acid. There's 1 mole of H3O plus per mole of HCl from the balance equation, right? This is way easier stoichiometry than stuff you've done. and that means we get this. All right. Then to calculate the pH, pH is the negative log of the H3O plus, which is the negative log of 0.020 in this case. So this is something you do on your calculator. Just take the log of 0.02 and then drop the negative. All right. Now, pH of a base. How do we do the pH of a base? Well, it turns out that in water, there's a relationship between hydronium and hydroxide, and this is experimental. All right, and the relationship is the product of them is equal to 1.00 times 10 to the minus 14. There's a mathematical transformation that you can go through. If you take the negative, if you're curious, take the negative log on each side and you'll get to here. You'll find that pH plus POH equals 14. This is the same equation really, it's just transformed. And if you're really interested, pop up on Zoom and I'll show you where that comes from. All right, but this is usually, people usually do it this way. So if it's a base, we want pH. So how do we do pH of a base? So let's go through it. So let's do pH of 0.03 molar barium hydroxide. So we start, same approach, balanced chemical equation. Barium hydroxide breaks into ions. We start with 0.030, nothing and nothing. We want to know what happens at the end. So the 0.030 becomes 0.030 barium, 1 to 1. 0.060 hydroxide because there's 2 hydroxides. So again, this is pretty straightforward stoichiometry. You've done stuff way harder than this. That means the hydroxide is 0.06. That means POH, which is negative log of OH, negative log of 0.06, which is 1.22, but that's the POH. pH plus POH is 14. That means pH is 14 minus POH. So 14 minus, in this case, 1.22 is 12.78. As far as sig figs, there is a rule for sig figs for logs. We're not going to do that. You can learn that in Chem 200. So just give me 2 decimal places. All right? That might very well be it. That's it. So at this point, you should be able to do homework 13, which is the second to the last homework. And this is stuff that'll be on exam 4 and on the final. Hope you're all well. If you have questions, pop up on Zoom.